Yes. So what did we do the last time? Yeah. So the last, yeah. So we were looking at these sequences, right? So where are we? Let's try to understand this. Yeah. So we saw I think the main thing was that we saw the importance. Yeah. We saw the importance of, wait. Yeah. We saw the importance of monotonic sequences. Yeah. Monotonic sequence. We saw that these are very important. We have not yet formally defined the notion of a limit of sequence, but we roughly understand that it's a point that it describes a sequence when the number of terms become large. Okay, so we did see that, and so that's why we are looking. So that's why we started to look, looking for monotonic sequences. This is the idea. Okay. So monotonic obviously here just means increasing or decreasing. Could be increasing or it could be decreasing. So we are looking for monotonic sequences, okay? And this is where combinatorics or pigeonhole principle, to be more specific, and if one wants to do it in an elementary way, comes in. Okay, so and this shows up in problems all places. So this is where the combinatorics will be used to show the presence of looking for monotonic sequences, or rather, to be more precise, looking for monotonic subsequences inside sequences. Okay, so because I'm using the word subsequences, let me actually precisely define what a subsequence means. So if you have a sequence, yeah, let's define this precisely. Obviously, a lot of interesting counting problems, algorithm problems related to subsequences comes up. So let us have a clear definition of it, prove some basic result that exists the monotonic subsequences, and then we can, yeah. So obviously, if you have a sequence x1, x2, just a random sequence, okay, as random as you can make it, okay. In fact, the idea of it is to show that there is actually no truly random sequence. Okay, there is no true randomness, does not exist. Is what basically philosophically we want to claim, and then we'll see it come up in different places. Same principle. So we have this sequence goes on and on and on, infinite. So all the sequences we are interested in are infinite because they are infinite. We are interested in the limits. Okay, because we want to be able to describe what happens when n becomes large. We want to understand what is the limit, so on. So that's the reason why we are studying them, because they're infinite sequences, okay? Infinite many terms. We have this now. What is a subsequence is very important to understand, because all the definitions in analysis, especially in if whenever there's a sense of distance there, can be said in terms of sequences and subsequences and so on. Okay, so subsequence. What is a subsequence? Okay, so subsequence would be basically you pick up a part of the sequence, an infinite part of the sequence, where you do not change the relative order, roughly speaking. Okay, so let's first just say roughly speaking. Okay, so not giving too much that motivation, because last time we did kind of see the sense of how you will get a part of a sequence will be monotonic and so on. Okay, and also I said how the part of a sequence can actually control the entire sequence, okay, in sense of a drag and something like that. But roughly speaking, let us just, so roughly speaking, we can at least first say part, I should say infinite part, but part of a sequence, okay, with same relative order. Now, these things like relative order and such also come up in combinatorics. We will see more about them, but for now, this is what it is. Okay, part of a sequence with the same relative order. Okay. So, what should be the formal definition? Yeah, well, the formal definition basically means that you take a part of the sequence. So that is, you take I1. That's first thing. That's the first term in our part. I2 is the second term in our part, and then we have I3, I4, and so on. Okay, so this is what it is. These are the indices. Okay, so we'll have these indices, and our subsequence is xi1, xi2, xi3. Okay. So if just for example, you could just take all the odd terms. Is it okay? Is the notations clear? Then in this case, what would I1, I2, I3 all be? This is, yeah. Then the I1 would be 1, right? And I2 would be 3. This would be 5. This would be 7, and so on. Okay, just a part, and just with the same relative order as it was in the original sequence. Okay, subsequences. Subsequences are also interesting because sometimes we are interested in the, like, instead of just understanding, because when you're looking at summations, we are looking at sequences, partial summations, sequence of partial sums. Okay, we're looking at those things, and it seems like everything is in those sequences, but sometimes we'll be looking at sets, and we'll try to understand a summation of a set. That's sort of what integration tries to do. And then different other things, limits of a set, and so on. And there we will study it through sequences in the set. And that's where subsequences become very convenient, make the things very simple. Okay. So this is just the definitions. Okay. Yeah. So let's just quickly state the result. Is the definition clear with everyone? Okay. Okay. So let us state the. Are there any questions? Okay. Okay. So let us just state the thing that we were trying to prove the last time. Okay. So we were trying to prove the last time that we are also given some motivation. So now we'll just state it. Maybe I do not know the name for this theorem, but this is, yeah, this comes packed with, so if you read an analysis book, hardcore analysis book, it will be called the Bolzano-Weierstrass theorem, but that is this along with something which we will say. This on its own, let's just say that what it means. Okay, theorem is that every infinite sequence has a monotonic subsequence. Okay, every infinite sequence has a monotonic subsequence. This is what we wanted to show the last time, right? That no matter how random your sequence is, there will be a part of it which will either be increasing, and now we understand rigorously what that part means. It will either be increasing, or there will be, if that doesn't happen, then there will be a part which will be decreasing. Okay. Now, before we go into the proof of it, has anybody thought of why such a result would be true? Without actually going into the proof, can you explain it? Can you explain a more general phenomena that is going on here? Okay, as to why this is true. So why is this true? Any sense as to why such things happen? So we have a very disorderly situation, right? Just an infinite sequence, disordered. You can make it as disorderly as you want. And then yet there is some sort of an order. Okay. So why will such a thing happen? Okay. We will also see this kind of result in graph theory, where this kind of thing happens. So why does this kind of thing happen? Has anybody given it a thought? Because we had seen this the last time, and there will be many results of this type. So this is the type of statement that says this is a order in chaos type of statement, right? It is basically saying, and it's reinforcing a general phenomenon in mathematics, that there is no true randomness, there is no true chaos. Okay, so you see, when we say monotonic subsequence, let's break this up, then you can understand, then we can maybe further, I can explain what I'm trying to say further. So either a increasing subsequence or, so the or is very, very important, okay, because we're not claiming that both of them happen, and obviously not, yeah, or a decreasing subsequence. Okay, so either there will be an increasing subsequence or there will be a decreasing subsequence. Okay, so you can kind of see that these two are kind of like complementary forces, opposing forces. Yeah, these two are complementary forces, these two are opposing forces. Okay, so if you're seeking chaos in one of them, if you're seeking chaos in the increasing part, okay, then there is an order in the decreasing part. And if you're seeking chaos in the decreasing part, then there will be an order in the increasing part. Why? Because if you're seeking chaos and infinite chaos, meaning that you go infinitely long, but still you'll never find a part, just a part even that is keeps on increasing, right? So this is a part where we are seeking an infinite. One second, someone is joining. Yeah, this is a part where you're seeking infinite chaos in some sense. Okay, and who forces that? This randomness here, which is infinite randomness, is forced by the decreasingness. It is the decreasingness from time to time is what forces this increasingness to not happen, right? So if you're seeking chaos in some sense, okay, then for that chaos to be maintained infinitely often, or for that chaos to be maintained, yeah, there has to be an opposing force that has to constantly work, right? But then that brings order in that opposing force because it has to constantly show up and do something. Okay, so you see, now it looks kind of okay, because in the opposing force has to constantly do something, so that's what brings the order in that. So just to prevent chaos in one part, in the complement that comes in order, and vice versa. So there cannot be a true chaos. Okay, if your system is in some sense, if your system has a notion of complement, okay, then there will not be. And this is just seen in all the places, graph theory and a lot of places. Okay, in general, it's a theory, but that's an advanced thing too. Then, means I myself have not studied, just a few theorems here and there. Okay. In any case, yeah, this is what I was trying to say. Okay, now let us actually, and this is actually the proof. This is actually what, if you see once we do the proof, we already seen part of it. This is what we were doing basically. So, yeah, now let us stop this thing. Let's actually get to the proof. Okay. Yeah. So the proof. So I hope some people have tried to prove this on their own, and maybe then you can share, because you can come up with, then maybe we'll have a new proof. Anyone has tried to prove this? This is a very significant statement. See, at the bottom of analysis, the statement is there, the combinatorial statement. Just like at the bottom of number theory, you have the Euclidean algorithm, which is an algorithm. It's basically a recursive thing, right? GCD of A comma B, GCD of B comma R, yeah, a quotient and remainder and so on. And just like that, this is at the basis, this is at the foundations. Again, a combinatorial result, set theoretic result, set theoretic result. Has anybody, because we had seen the idea last time, right? Has anybody tried? Please try these things. spend time, think about this. Obviously, I should get more problems actually. I should actually get more problems also. But this is also an interesting thing to think about. Right? Okay. Okay, so no one maybe has. Okay, no problem. Let us try it. Okay. So how do we prove it? I mean, how do you, and in general, this is the things that we learn through these proofs, right? These theorems. In general, how do you prove such a statement? And this is kind of statement, let me not write monotonic here. This is not, it's good for writing, but to understand, you should write it as has okay, sequence either has an increasing subsequence or this is or a decreasing subsequence. Okay, so it will either has an increasing subsequence or a decreasing subsequence. Okay, so in general you will have many statements like this. Okay, either three people know each other, all three know each other, or none of them know each other. There will exist some three people like that. Many statements are like this, either this will divide that or this is the co-prime to that, something like that. Okay, so how do you show in general, how do you start? I will not say show because I don't know how to show all of them, but how do you start? How do you start? I mean, typically, how do you start such proofs? So that you have a good, so that you're starting with a good, set of assumptions. Healthy such a set of assumptions which you can play around with. Yes, certainly. So certainly we have to go by contradiction. That is true. That is true. Certainly the proof will be by contradiction. That is clear. Because there is no way you can actually construct and that subsequence, because even we don't know what the sequence is, right? We do not know what the sequence is. And this is another very, I would say, something that comes up. That's right. Yeah. What are the two parts? Yes. That's right. That every sequence has a monoton, has a convergence of sequence. Yes. So that is a very compact way to write it. That's correct. Yeah, that's what we will get to. But this is at the heart of it. It is this, because once you have monotonic part, then monotonic part converges will be obvious once you have the definition of converges. Okay, it's just supremum. But in any case, that is not exactly what we're doing now. But this is the foundation of it. And we want to see this not just for analysis purpose, but we want to understand the pigeonhole principle behind it. We want to understand this randomness and so on, so that when we do the same result in other places, we'll just do a finite version of that, which is a theorem by Erdos. That is also a very, it used to be a good contest problem. Now it is so much repeated that it doesn't come up. But we'll see those things first. Okay, then we'll go to the analysis maybe next week. So we have this x1, x2, x. So what I was saying is, yeah, that x1, x2, x3, and so on are there, right? And point is that, see, in this, there will be a monotonic subsequence we want to show, but we do not want to find that monotonic subsequence. Okay, you cannot find that sequence. Okay, you cannot describe it. You cannot say that if this is a sequence and that will be, x2, x3, xp, primes. Absolutely. Yeah, it is something like that. So your bits and parts is obviously correct. Yeah, no, but I am trying to just, a more trivial point I would say is that, because when you get a question, right, you should, I mean, you would immediately know after some time. We are, depends on the level and so on. Point is that you should ask yourself, can I actually construct a sequence? Can I actually construct this thing that is being asked? Will I end up with a formula? Will I end up with a description, an algorithmic description? of how to get that sequence, okay? And if your answer seems to be no, then you would have to go by contradiction, okay? Because if you do a proof straight away, straightforward means in the sense that it's not straightforward, but direct proof, constructive proof, right? Then then in the end, you will arrive at something, arrive at a sequence, a subsequence, some kind of an algorithm or a description, okay? But because such things don't simply exist in this case, okay? So you would have to do a proof which is non-constructive, which is contradiction. Okay, so you assume that it doesn't exist, and that assumption is wrong. Okay, that was my just small point. So the proof by contradiction is very, very obvious. But the second thing, which is very important in these kind of statements, just to get you started, maybe, is that assume that one of them is false, which is essentially what proof by contradiction. But here is the thing: assume that. Okay, if you just assume that there is no increasing and no decreasing, then you want to get some contradiction. Very good. But how do you do it? But that is not needed. And that is not very sensible thing to do here. Here, if you just assume that there is no increasing subsequence, okay? And obviously here, subsequence means infinite, okay? No, I will not say that. Without loss of generality, right? No. It's not. How is it? How is it a loss of generality? How is it not a loss of generality? Because I mean, because both of them may not exist. I mean, it's not like if one of the increasing exists, then by symmetry other also exists, or I don't know. Okay, you have to explain if you're saying not a loss of generality. But this is a very straightforward thing. Assume that one of them does not exist. Okay, assume that there is no, and that's the opposing force thing, right? If there is no increasing with the decreasing one is opposing, then that will be decreasing infinite decreasing. A very obvious thing, but yeah, this is what we should start with this kind of statement. Assume that one of them is not true. So assume that there is no increasing subsequence. Okay? Then we want to show that there is a decreasing subsequence. Okay, so we want to show that there is a decreasing subsequence. Okay? How do we do that? Yes, now maybe if someone, I'll just draw a picture. Just so this is one. Just like last time, these are the terms and the actual sequences above. So how should we? So there is no increasing subsequence. Means that if you start from anywhere, you can't keep increasing forever. Even if you're skipping the things. Yeah, it's not like continuously you cannot increase. No, not just that. You cannot. So you have this, now you find something way afterwards and then way afterwards. If you keep doing this, you will come to a stop. You will come to a place where you cannot keep doing it. No matter how you do it, no matter how you pick these things, if you want to keep climbing up, you will not succeed. You will have to stop at some point. That is what not having an increasing subsequence means. Yeah. So they will have to be. So what does that mean? We'll have to stop. Let's try to say this in a different way. I'll just say it slightly different way. It means basically that if you start with x1, let's say, and then you ask, do I have a term after this which is bigger than x1? Okay, maybe you find some term like that. Okay, and then you ask, do I have a term after this which is bigger than this x4? Maybe you'll find this. Okay, but after some point, you cannot find a term which is bigger and to the right. Okay, that is what it is, right? So you cannot keep finding terms which are bigger. Okay, so let I1, okay, be such that xi1 is bigger than xj for all j bigger than I1. Okay, so there is a place there's a place I1 which is sort of like the maximum, may not be the maximum, but it's kind of like the maximum, right? I mean, at least if you're interested in the things to the right, it is a maximum. Or you can just pick the maximum also. So this also proves that there will be a maximum term in this. Okay, because to the right you can find the maximum, and this is the maximum for everything to the right. And to the left you can find the maximum. So this xi1 is like the peak. Okay, it's a peak. Okay, this is peak 1. xi1 is peak 1. What do we do next? And if it's something is not clear, please ask, because it's a very crucial proof. It's a very crucial theorem, and we would want to understand. It's a peak. Okay, you do not increase further, at least if you go to the right. So remember, we want to show that there is a decreasing subsequence. Okay, so it means that the next term will be less. Not just the next term, but any term. Yeah, any term here, the sequence is, the entire sequence is inside, is below this line. This line keeps going on. So this opposing force does not allow the sequence to rise above xi1. All right. So it will fall, right? It means that it will keep falling, right? Sorry. But it doesn't have to go to. The sequence can be a bounded sequence, right? The sequence can be some all rationals is something like that. Yeah. So that is right. The sequence, the number of terms is unbounded, but the sequence itself may not be bounded. And you do not have to be unbounded to get to a, so you can get a decreasing sequence like this, which is not unbounded, but it's not going to minus infinity, but it's still decreasing and infinite. Okay, that can happen. Yeah. But now it's very simple, because from here you can repeat the same process that you already did from the beginning. Just repeat the same thing. Just iterate. Just repeat the same thing, right? I mean, obviously, to find this I1, you do not know how far you have to go. You may have to go to 10 to the power 10 terms. And that's why this is algorithmically not a feasible thing to do. Okay, maybe you could describe it algorithmically, but it's not a feasible thing to do. Okay, so, but if you just repeat what you already did, meaning that from I1, let's leave I1 alone, leave it. You look at I1 plus 1, right? Take I1 plus 1. Now you look at a term which is bigger than I1 plus 1. Maybe you find something, and then something which is bigger than that. Maybe you find something. And once again, this process has to stop. Once again, it has to stop because the opposing force will not allow an increasing infinite process. Okay, so it has to stop. And once again, when this stops, you get an I2. You get an I2. What is the property of I2? That nothing to the right is bigger than it. Just the same thing as I1, okay, but just I2. So you get an I2, right? You get an I2 in the same way. You start with I1 plus 1, you keep seeking bigger terms to the right. I'm not saying immediate right, but keep seeking for bigger terms. And you will have to stop because there is no increasing infinite. Infinite, I mean infinite terms, obviously. There's no increasing subsequence. And so you stop, and then you get the second peak. But this peak is less. This peak has to be less than the first peak, right? So this is very clear because by the very definition, right, xi1 is bigger than xi2, or maybe bigger than equal to, well, that is not up, that is okay, a non-decreasing. And in this way, you continue, you will keep getting xi3, xi4, and so on. Just repeat the same thing. And this way, you'll get your decreasing. These peaks, as one way to put it. Is it fine? Is it okay? So if you have an infinite sequence, then you have an infinite monotonic subsequence inside it. Please make sure the proof is clear. Last part, meaning xi2. Okay. Yeah, please say. Yeah, first you should. So see the first box that I've drawn. Yeah, this just says that all the terms after I1 are less than xi1. Yeah. For all j bigger than I1, xj is less than or equal to, that doesn't matter, xi1. Okay. It is clear that that is true, right? There will come a time when you will find such an I1, because if you don't find such an I1, then you'll get an increasing subsequence. Right. What did we start with? Yeah, we started with this, then we are looking for a bigger term. We found a bigger term. Maybe after 100 terms we found, but we found. Then after 1 million terms, we found another bigger term. But then it has to stop. You can't keep finding bigger terms. That's what increasing subsequence, not having an increasing subsequence means. So it means that you will have to stop at this point. And then you repeat the same thing from here, from the next I1 plus 1. And then you get another such thing, I2, which has to be less than I1, but that's the definition of I1. And in this way, you see, you keep getting a decreasing subsequence. So we try to avoid an increasing subsequence, but we got a decreasing subsequence because this obviously we can continue as long as we want. Okay. So this is a very subtle result. Okay, it's by no means very obvious. I tried to say it in a way before the theorem that opposing force and so on, but it is still not obvious. This result is, yeah, but yeah. So let me not go to the Bolzano-Vias trust thing so on today. Let us actually look at the finite reincarnation of this result, okay, which is actually, I would say it's a little more difficult to prove, but it's a very interesting standard exercise, not exercise, but example, I would say first. Could be an exercise also in Pigeonhole principle, okay. So let us do that. That's a very typical example. So we have shown that every infinite sequence has a monotonic subsequence. But now this result was known for a very long time, okay, has a monotonic subsequence. But then people asked, okay, one second. So this is again a qualitative result, okay. It's more like a qualitative result, right? We are not asking for the frequency of the terms of the subsequence and so on and so on. We're not asking for the density of the terms and subsequence and so on. We're just having a monotonic subsequence. It could be very sparse sequence. It could be sequence of squares. It could be like x1, x4, x9, and so on. Very few, very far space terms and so on. We're not asking for anything. Okay. But then combinatorialists and so on took this one step further and they asked, what if we have a finite sequence, okay? Or rather, they asked like this: if I want monotonic, so remember, we can only ask for a monotonic. You cannot ask for an increasing or decreasing. If you say I want an increasing subsequence, then you can never get it. If you just take a decreasing sequence to start with, you can't get. Okay, so when we ask for this order in chaos, we have to take the complement into account. So we have to take notions which have complements. So monotonic is such a notion, it's a complete notion. It has a complement in it. It allows for complement. So if I want, so this is what they asked. If I want a monotonic sequence, okay, I don't want an infinite, but if I want a monotonic sequence of length, let's just take a very silly, simple example, very simple example, but length 2. Let's say if I want a monotonic sequence, subsequence, or just a subsequence of length 2, then how long sequence should I take? How long a sequence should I take so that no matter what that sequence is, I will get a monotonic subsequence of length 2? Any quick answer? Here we saw that if you take an infinitely long sequence, then you get an infinitely long subsequence. Very good, which is monotonic. But now we are asking a qualitative version. If I want a monotonic subsequence of length 2, then how long sequence should I take? Quickly, this is a very trivial question. I mean, some may have problem absorbing the language. That's fine, but otherwise, it's a very trivial question. Let's just, why length 4? You just take length 2. Yeah, obviously, length 4 will obviously work, but just take length 2, right? Because I mean, if you just take a sequence x1, x2, then this will either be x1 will either be less than x2 or bigger, and whatever. You will obviously have length 2 is trivial. Yeah, just take 2 terms and that's it. Yeah. Is it okay? This is very trivial. Then what they asked, let us just not go get to rush, because we really want to understand, because when this comes up in graph theory, this will become more complicated. Okay, I'm saying it as graph theory, but it's just basically in combinatorics books, it will be in pigeonhole principle chapter. Okay, mostly if it's a I don't know. Yeah, so if I want a monotonic subsequence of length, let's make it 3. Okay, then the question is, how long should I take? Now, before someone answers this, my point is, see this, what does it mean? It means that no matter what sequence I take, that is the thing, no matter what sequence I take of that length, and that is the gut feeling, is that it should be possible. Yeah, if I take a long enough sequence, then I should get 3 terms which are either increasing or decreasing. Yeah. For example, if I take an infinitely long sequence, then it will definitely work. Okay, analysis people are happy with that. But the combinatorial said, the algorithmic people, they're saying, no, can you give me a bound? Can you tell me how long sequence should I take? Obviously, 1 million will work, but can you give me a smaller number of terms, a smaller number? Okay, so that if I take a sequence that big, then I will get at least 3 terms which will be increasing or which will be decreasing. So yeah, let us do this. So you guys can just try out with 4. Can you make a sequence of length 4 which does not have? So your challenge will be to make a sequence of length 4, 5, and so on, which does not have a length 3 monotonic subsequence. Right? And then you see how long you can keep doing it. And at some point, you will not be able to do it. And then that will be your answer. That, okay, now this is the length for which no matter what I do, I am getting a 3 length subsequence. Okay, let's try length 3. Length 3. Length 3 obviously does not work. Yeah, you can just take 1 minus 1 and 3. You see, there is no subsequence of length 3 here, which is increasing, obviously, or decreasing. Yeah, it's a zigzag. Length 4, anyone? Very simple. So this is just up, down, up. There is no subsequence. Subsequence of length 3 would, which is increasing, would be like this, or falling. 4 should not be hard. Just take a zigzag. I mean, just simple, right? Just take any zigzag will work, right? Just take anything. Zero after what was after 0? 7, 9 and 2. Yeah, just any. Yeah, right. This certainly no, no. Yeah. Uh, okay. Yeah, so something like this. This also, yeah, so works. Maybe that would also work. Yeah, but this also works, right? So this decrease and then increase and increase. Yeah. So, but then what about length 5? Can we make in length 5? Which so we are trying to avoid. We're trying to avoid this pattern, length 3 pattern. Actually, that's a rigorous term pattern, but for now it is just a term. No, we are trying to avoid getting length 3. So maybe the word pattern is not suited here. Okay, I'll just say we're trying to avoid this. We're trying to avoid a length 3 monotonic subsequence, right? We're trying to avoid this. Hmm? No, but okay, tell me one more term and see if we can. What? See, but we are caught. If you take 5, then it doesn't work because then you get an increasing subsequence of length 3. So we can't avoid. It seems like. So it seems like you cannot avoid. You see, it's already clear, right? Yeah, because if you try to or not, yeah, it's very clear, right? Is it clear to everyone? Like if you try to avoid it in the first 3, then it says you have to make a, you have to make a down, up, down. For the next one, if you make down, then that's gone. If you make, and if you make, I mean, if you make up, then maybe, but then you have to come down again, and you can just take cases. Yeah, if you just, you can just take cases to it. Either way, you'll see that you will get a, and if you go too much down, then there will be a, you can make cases and prove that. It's very simple. That so 5 is a number. Okay. So for length 3, for L equal to 3, and no, maybe I should not use any notation, just not use any, let's not use any notation, confusing. So for 3, so for 2, 2 is enough. For 3, we need 5. Yeah. So, but at least I think you guys will get the intuition that if I make this length any number, once again, if I make this length any number k, yeah, then for this number k here, you can give me some number. I don't want infinity. Infinity will certainly work, but can you give a number? And later on, we can think about, can you give a best number? Okay, like here 5 is the best number. You could have given, if you could have said 50. 50 is correct. Yeah, if you have a length 50 sequence, then obviously it will have 3 increasing subsequence of length 3 or decreasing subsequence of length 3. But 5 is the best one because for 4 and 3 we showed it is not possible sometimes, like we have already created examples. Okay, obviously for 4 also it's sometimes possible. I mean, obviously you just take this thing pleasing, but it's not always true. But for 5 it is always true. 5 is the smallest. Okay, so in general for k, okay, what is that? Sorry. Just for these, okay, 3k minus 4. So can anybody prove him wrong? If you can, because it may not be easy actually. This can be actually a first part, like to find a sequence of length 3k minus. Let's even take 3k. Okay, let's not forget about 3k minus 4. 3k is even better. Even if you prove that this is wrong, then that's also wrong. So 3k. So given a sequence of length 3k. Okay, I just say find, or then, or if I'm wrong, then prove it. I mean, okay, find a sequence of length 3k. So you have given 3k terms, okay, with no monotonic sequence, no monotonic subsequence of length k, or more than that. More than that means you will have k. So you do not want to increase beyond k terms. You're okay with increasing up till k minus 1 terms, but don't want to increase further. Can anybody quickly make an example? Just writing it like this makes it clear for me that this is not possible. But I'll also think of a concrete examples, and you guys also think. No, it's not hard. So you want to make a sequence of length 3k. You can take k to be 10 if you want to, something, but we do not want a monotonic sequence of length k. No, see, if it's more than k, then it will have k also, right? You can just take the part of it. So yeah. So all monotonic sequences, subsequences should be length less than k. Yeah. So that dot thing that I was drawing, you can just think using that, or using any other model you have, and then share it. That's most interesting. Yeah. Yes. To make it, to find a sequence. Okay. But pigeonhole principle will never tell you that something is possible. Pigeonhole principle will always tell you that something is not possible. I mean, yeah. Okay. Let's see. Hmm. Okay. No, but so okay. Box 1 and box 2. So can you describe it more? What is box 1? What is that? Is a increasing sequence. The box 1 is just one increasing sequence. Okay. So I can take any increasing sequence, just 1, 2, 3 till length k. Okay. Okay. So you can take 2k plus 1, 2k, 2k minus 1 till k plus 1. So okay. No. See, but if you start with an arbitrary sequence of length 3k, then how will you distribute? Because some of your sequences that you start with, they may have monotonic subsequences of length k, but we want to show that all subsequences will not have that property. Yeah. So if you want to show, right, we want, so pigeonhole, if you prove this by the pigeonhole principle, will always tell you something like no matter what you do, you will have a subsequence of length k, right? But it will never tell you the opposite. That is, if there is a sequence for which this fails, then making that sequence pigeonhole principle will never tell you. Or but see, this is very easy. See, you can easily just make this sequence. Yeah, just make it. You already have also you already made it. Just make it like this. Yeah, just take 1, 2, 3, 4 till k terms. This is k terms. Okay, x1, x2, just increase them. Okay, and then just decrease them. Just do the same copy again, right? And let's do the same thing again. Simple. So just take 1, 2, 3 till k, and just do again 1, 2, 3 till k, and again. So does it have an increasing? Okay. No. So I meant, yeah, sorry. So this is, I meant k minus, you can take k minus 1. You can take k minus 1, and then in the end, you just put a few more terms, 3 more terms, something like that, right? Yeah, yes. I mean, k plus 1, this would work, but yeah. Doesn't matter. This k has to go. So you guys understand, right? This will not have a monotonic subsequence of, just take 1, 2, 3. So is there a monotonic sequence of length k? First of all, is there an increasing sequence of length k? Increasing subsequence of length k in this? Why not? But see, that is not a problem even, right? You can just take this as 1.5, 2.5, 3.5, something like that. That doesn't matter. You can just make that, you can tweak it. If you can tweak it if you don't want it to be constant. But even then, no. But when I say increasing, I mean that it non-decreasing is also fine. Okay, that's also I'll take as increasing. Maybe. Oh, then there is a problem. There's a yeah, so you can just tweak it a little bit. Just take this minus half, just take this minus 1/3, something like that. Okay, you see. Where? So do you have an increasing sequence of length k? After this, where is the after this? You can't go back. That is the whole point. Right. Yeah. That's the whole point. You can't go back. Subsequence means you have to keep moving forward. You may not visit all the consecutively, but you have to keep moving forward. So see this obviously, and this is a very simple example, right? It's nothing. Just check that this doesn't have an increasing subsequence of length k, which is obvious, and also it doesn't have a decreasing subsequence of length k. Check that also. That's more obvious mostly. Okay, but yeah, just write it out. Maybe then just practice in writing mostly. But you should also be able to write it so that you don't. So when you write, you would understand whether you're able to get your ideas across crisply, right? So that you don't end up in cases, okay, one more case, and then you forgot some case. So writing is very, very important, okay? 40% of your success in the exam depends on writing, okay? If you can write well, explain all things that you've thought about, and not every damn thing you think you write, no, but you see, understand, right? How you get your ideas across is very, very important. Okay? So write these things. This is very simple. The 3K will not make the cut. 3K will not make the cut. Okay. Yeah, it is something like that. That's perfectly right. We will need k square and things of that nature. Okay. So let me just, so now one can do this in a more investigative way, but we have finite time. So let me just say k plus 1. So if you have if I want a monotonic subsequence of length k plus 1, then this is k square. Okay. Now let me say this statement in a different way. This is how it was asked. So this means that if you take a sequence of length k square, or maybe, wait, is it k square or k square plus 1? I think k square is for k plus 1, k square will not work. I can give an example. I'll ask you guys to construct that, but let me first state the result. Yeah. If I want a monotonic subsequence of length subsequence, let's write it fully, respectively. It's very important. Increasing subsequence of length k plus 1, then how long should I take my sequence? It should be length k square plus 1. This means that if you take any sequence of length k square plus 1, it will have a monotonic subsequence of length k plus 1. That's what it means. Okay. So let me write that version also. Any sequence of length k² plus 1 has a monotonic length. So I would say at least k plus 1. It could have more also, but then it would have that also. So it's the same thing. I should not actually say at least of length k plus 1. Okay, this is what we want to show. And k² is not enough. So think of again, try this out. Okay, you can take some concrete numbers and do. Think of a sequence of. No, we need to prove it. We want to show that for any k, in the sense that it depends on how the question is asked. If it's asked like prove that for any k, so that's more than that, right? Prove that for any k, if you want a subsequence of length k plus 1, then taking k² terms will not be enough. For any k you want to show. Okay, so maybe that is also a thing that one can try. Okay, so try to show that k² is not enough. It has to do with something grids and such. Just think about it. It's not very difficult, but it's not the most trivial thing also. Okay, take some, maybe you can take examples k equal to 5, and then you can try to actually make a sequence. It's very, very important to make counter examples, because understanding counter examples helps you to understand the theory itself and the limits of the theory more than anything. Okay, if there are interesting, if there are interesting counter examples and such, that can tell you the extent of where things can be and so on. Okay, so this is the thing. So this is what we want to show. Okay, so let us not do it today. We're almost out of time. I don't want to start this again, this thing today. So, but please try to show this. Okay, try this on your own. This is a very standard result, but try it on your own. Try it on your own. Okay, and let us then discuss it the next time. Okay. And meanwhile, let me just discuss one of the problems I'd given the last time, and then actually last before that, and then it had got messed up. So let me discuss that. But please try this. It's not an easy result to prove, but most importantly, we are understanding the perspectives, okay, from which we are looking at it, okay, and these kind of questions, how they come, and so on. So, okay, let me just discuss that problem that looking at. Okay, so what we were looking at is color the points of R2 with two colors, okay, such that, so first you must make the coloring first, okay, such that given any set of lines, 1 minute, given any set of, yeah, the next class I will also do some, I'll also give some problems which are more contest. These are also contest problem, but these are on the harder side, okay, so I'll also give some more standard questions and references. That was in my thing, but I didn't do it. So, yeah, I'll do it next time. So that any set of lines cannot distinguish the colors, cannot distinguish the colors. Okay, now what do I mean by this? Okay, I mean that if you take, so you have to first do the coloring such that now you take any set of lines. So maybe take like this, and you take any set of lines. Okay, any set of, so I should say finite. I don't want to say infinite. I mean, infinite is not something which you should think about even right now, but just as thinking, if I take infinite, I shouldn't take infinite, then you can just do anything. Yeah, no, that's wrong. Yeah, so one second, let me just also state this question more clearly. So my point is that if you take any set of lines, so if you take any set of lines, then it will have intersections and such, right? And after you've looked at all the intersections, yeah, you will see that it kind of partitions the plane into several pieces. Yeah, several pieces. Okay. Then what I want to show is that what I want to say is that your coloring must be such. Your coloring must be such that in any piece, yeah, in any piece, you would have both the colors. In any piece, there will be a point which will be black, and there will be a point which will be red. And you have to first do the coloring so that no matter how I place my lines, okay, and the pieces that are formed, every piece should have both the colors. Okay, so it should not be like there is a piece which is completely red, and then there's a piece which is completely black. Don't want that. Okay. Okay. So Raghav, what were you saying? Coordinates. Yes, that was very simple. Yeah, so that was what Rishabh had also given the answer to, that if you just take, yeah. But then, and has anybody thought about this version of it? And this is very much to do with rationals being, everywhere. See, if we want our coloring to be such that it is everywhere spread out, so we want a uniform coloring which is spread out everywhere, which uses black, red, everywhere it is there. Everywhere you look at, there's a black and there's a red. Every small place where you put your microscope on, there is a black and there's a red, both there. That's what we want, right? So how do you color things so that many ways to do it? You see, the point is that yes. But you should say, like, if there is a point which has both rational coordinates, because now there are coordinates, right? Yeah. So if x comma y such, yeah, you can, yeah, it doesn't matter, yeah, such that, no, we don't want to, that will work, that will certainly work, you're saying will work, but I can just we can just say it more simply. If x and y are such that x and y, but that will work, yeah, are both rational, okay, then black. Okay, so 1 comma 1, 2 comma 2, 3 comma 3, half comma half, and so on. Or I want to say half comma 49 by 53, all are black. Okay, the rest are red. That's what you do. Okay, now what is the idea of this? See, what we had seen, let me just go back and make this very clear. What did we see the last time? Last time we saw that if you take if you take any real number x and you take any small, no matter how small that interval is, you will find a rational point. You will find a rational number here, right, in that neighborhood. Yeah. In the same way, if you take any point in the plane, right, and you make a ball, try to write these things, you make a ball. Yeah. If you take a point in the plane, any point you make a ball, any ball you make. Yeah. Any ball you make, you can find a point inside the ball which has both rational coordinates. It is exactly this what I said. It is much simpler than that. It's, you can, in the sense that it is the same thing, but I'm saying that given any real number x or any point x, yeah, you can make a neighborhood, and sorry, given any point x and any neighborhood you make, there will be a rational number in that neighborhood. Okay, that is what I'm saying. Now use this. If you use this, you can prove this also, that given any point in any neighborhood, you can find a point which has both rational coordinates, q. Okay, q has both coordinates rational. It is not hard to prove. It is not hard to prove. It's very easy to prove. I'll just still say the proof because this is maybe a new kind of thing. So if you just take a point, take a neighborhood, right? Any point, you see, you've taken a neighborhood like the ball, an open ball, right? A radius, any radius around X. You see, along this line, you can find a rational. You know that. You guys know that, right? That's what we already proved. That is what it's just exactly this. Yeah, just take X and take a horizontal line. Yeah. So you forget about the Y coordinates. Look at the X coordinate, right? So you can find a point Y here, and the X coordinate of Y is rational. Yeah. X coordinate of Y is rational. Yeah, X coordinate of the point. Maybe it's not a good labeling. I'll just say U and V. Yeah, the X coordinate of V is rational. Yeah, that is just exactly the same thing. Just forget about the Y coordinates and just look at the X coordinate. Okay. Now about V, you have this neighborhood. Here is also a neighborhood. Now on this, you can find, yeah, on this, you can find a point whose Y coordinate is rational. X coordinate will obviously be rational for all the things on that line, right? Because they are all having the same X coordinate. You can find a point where the Y coordinate is also rational, and then that is your point. Okay, so you can find that. You can find a black point. So that's what it means, right? Now, what is this? What is happening? Now, if I take any chamber, let's say I take this chamber, okay, I take this chamber, I take a point in this chamber, I can obviously make a neighborhood which will avoid all the lines. Is it right? Because I can take the smallest distance from all the lines. I can take the distance from all the lines and take the smallest distance. I can take less than that, right? And then because there are finitely many lines, and then you can make a neighborhood. Now, if that point is black, red, I don't know. But then let's, I mean, yeah, you can find a red point. Yeah, you can find a red point there. Doesn't matter. You can find a red point. So you can find a black. You can find a black point, right? Because you can find a thing which is, you take any point, you can take a neighborhood, you can find a black point, right? So you can find a black, you may start with, I don't know what color, and take a neighbor, but you can find a black point. And similarly show that you can find a red point also, because the other set is also dense. The other set has the same property. We also showed that for irrational numbers. Okay. So yeah, that's what it is. Okay. It is slightly complicated, maybe some of you, doesn't matter, but has everybody understood this, the idea? Otherwise, I'll say it again, whatever parts are needed. It's okay. Okay, is it clear to everyone? Just take your time, take a minute and think about it, and then we can see. Okay. Oh yeah, that part. Oh, right at the beginning. Yeah, so that was a slightly philosophical thing. So maybe I'll not say it this time. When I'll do the same thing in the graph theory class from a graph theory angle, then I'll say it. Okay, so because it will not be very useful now. Okay, yeah. Okay, so that's, but this proof is, I hope it's okay. Either way, some of you also missed the class. I'll upload this on YouTube. So some of you have missed it because timing change. So okay, so then it is clear to everyone. Okay, all right, then we can stop for today. Okay, then thanks.